Welcome back. This is the second lecture in the series. Today we're going to talk about two of the most important rules in electronics. We're going to talk about Kirchhoff's voltage law and Kirchhoff's current law. Before we do, let's review. You remember the symbols. We had the battery. The battery has polarity. The large bar would indicate the positive terminal. The lower or the smaller bar would indicate the negative. You may see a plus sign like so. We had a voltage source. And this is an ideal voltage source. We have current sources. Amp meters with an A. And voltmeters with a V. Something very important about these that I'll remind you again and again as we proceed is that current passes through the ammeter. So current through, whereas the voltmeter, it's voltage across. We briefly talked about circuits. Here's the ammeter with the current flowing through it. A switch, one resistor, and then a second resistor. So you would call this R1 and R2, switch 1. We could add a voltmeter. For example, if we wanted, we could measure the voltage across R2. We could add a second voltmeter if we like, and measure the voltage across R1. Something to realize, it's current through, and that current has a direction. In this case, we're going from our source to our load. And it's voltage across. This voltmeter is measuring the voltage across R1, and this one is measuring the voltage across R2. We introduced Ohm's law, and you recall we showed that as a circle, and we talked about the cover-up method. We also introduced power, again, as a circle with the cover-up method. Voltage, you'll see this as E, sometimes as V, is equal to IR. Current is equal to a voltage divided by a resistance. Resistance is equal to a voltage divided by a current. And on this side, power is equal to a current by a voltage. Current is equal to power divided by voltage, and voltage is equal to power divided by current. There are some shortcuts you can take to this. You could also say that power is equal to current squared R, and you'll see that referred to as I squared R. And power is also equal to the voltage squared divided by the resistance. We talked about subscripts with regards to measuring voltage. For example, if you had an element with terminals A to B, and if you were to measure 12 volts DC with your probe situated like so, and if there was a current of 3 amps flowing through this device, we would say the voltage A with respect to B is 12 volts DC. We would say the current is flowing in the direction of B to A is 3 amps. We could put these together and we would say there are 36 watts. Now the trick is you have to ask yourself, is this being supplied or is this being consumed? If the subscripts are different, then the power is being supplied. Here's another way of looking at that. If we had a power supply powering a resistor, and we said the supply was 12 volts DC, a voltmeter would read 12 volts DC. A current, a current would flow in the circuit like so. You could consider this point A and this point B. So there's a voltage, A to B is 12 volts DC. That's true whether you're talking about the power supply on the right or the resistor on the left. The voltage A with respect to B is 12 volts DC. But the current is different. The current on the supply is a current B in the direction of A, and we'll call that 3 amps. The current on the resistor is a current A in the direction of B, equals 3 amps. Again, if we look at the subscripts, AB, AB, we would say the resistor consumes and the supply, well, supplies. And if we go back to this one, we see that we have a voltage, A to B, and we have a current, B in the direction of A. So the subscripts are different. Therefore, what we drew above is this piece right here. It is a supply. We mentioned energy, and we define that as the product of power and time. Power could be expressed as the product of voltage and current. This particular form is useful if we're dealing with batteries and calculating the energy on the battery. You recall that the capacity of a battery was measured in amp hours. So if you had a 250 amp hour battery and that battery was 12 volts DC, well, the energy in that battery is 250 amp hours by 12 volts, which gives you 3 kilowatt hours. The last thing we talked about in the last lecture was electricity and the fact that it is sold in units of kilowatt hours. So you might have an electric price like this. So in this case, you might purchase electricity at 15 cents per kilowatt hour. Now we move to the next part of chapter 1, where we talk about Kirchhoff's current law and Kirchhoff's voltage law. We'll start with KCL. This tells us that the summation of the currents is equal to 0. We would read this as the sum of the currents must equal 0. Another way of saying that is to say that the goes intos, the current in, must equal the goes outos, the current out. This statement is true for the nodes in a circuit. What I'm going to do now is I'm going to go to a simulator and show you what we mean by the word node. This particular program is called Multisim, and I'll give you a quick demo of how it works. We start by establishing a voltage source. In this case, we may as well let it be 120 volts, and we'll set that to RMS. We'll talk about what that means later. We will establish a ground reference. And all of our measurements will be made relative to this. All right, so this is our 0 node. You'll notice how it puts a 0 right there. Resistors. Notice that number 1 right there. That is a node. Copy the resistors. We'll go grab a capacitor just for the fun of it. And we'll grab an inductor, because why not? Now we put these together like so. When we connect those up, notice that's node 2. When we connect the capacitor, no, it didn't give us a number, did it? Because that means that everything here, both this resistor and this capacitor, are on the same node. We connect this up. There's node 3. And this goes back to ground. And this goes to ground as well. So how many nodes are there in the circuit? So the nodes, we can circle them here. So again, this is one node here. This is the second node, the third node, and this was the ground node. Let's try a slightly different one now. So how many nodes in this circuit? And the answer is, well, there's 2. There's this one down here, which is our reference node, and then this one is our second node. So we have a ground node, and then this node on top of the power supply. Let's do one that's slightly more complicated. Let's grab this and circle those nodes. All right, node 1, node 2, node 3, and the ground node is down here. The important part is that Kirchhoff's current law tells us that the summation of the currents entering or leaving a node is equal to 0. For example, if we had a power supply, a resistor, a resistor, a resistor, a capacitor, and just for fun, let's erase this, and we'll put in an inductor. There are 1, 2, 3, 4, 5 nodes in this particular circuit. Kirchhoff's current law tells us that when we are on any one of these nodes, the currents into is equal to the currents out of. This middle node might have a current flowing in, a current flowing out, and a current flowing out. The summation of the current in is equal to the summation of the current out. In this case, we have 1 in and 2 outs. Here's another circuit. It has a constant current source and 1 resistor, 2 resistor, 3 resistor. How many nodes do you see? Well, there's only 2. There's a node there, and there's a node there. In this top node, we have a current going in, a current going out, a current going out, and a current going out. Again, KCL tells us that the summation of the currents on that node is equal to 0. One more circuit for good measure. All right, what do you think? How many nodes does this circuit have? There's 1 there, 2, 3, and 4 nodes in this particular circuit. 1, 2, 3, 4. Before I forget, I should mention that one of the nodes, we often establish that as the reference node, and we add this ground symbol to it, typically in this position here. And you'll see that on your schematics. So that is the reference or the ground node. But that doesn't change how many nodes there are. This first circuit still has 1, 2, 3, 4, 5. This one has 1, 2 nodes, and this one has 1, 2, 3, 4 nodes. Once again, KCL, which is Kirchhoff's current law, tells us that for any node, the summation of the current is equal to 0. Suppose we had a node that had 7 amps flowing in, 2 amps flowing out, and X amps flowing out. What is the total current? The summation of the currents in is equal to the summation of the current out. Here we have 7 in and 2 plus X leaving. So X must be equal to 5 amps in the direction that it's shown. So it's 5 amps in the downward direction. Here's another one. So we have a node. It has 1 amp flowing in, 2 amps flowing in, 3 amps flowing in, and X flowing in. Once again, the summation of the current in is equal to the summation of the current out. In this case, we have 2 plus 1 plus 3 plus X all going in, which means our current out, which means X in this case is negative 6 amperes, which is kind of interesting because that means that it's 6 amps but negative 6 amps flowing in, or another way of saying that is it's 6 amps flowing out. But that's not what we said, because we said that this particular current was going in, right? So this would be read as negative 6 amps. You may have seen this in the lab if you had your current meter hooked up backwards. So if you flip the 2 wires, instead of reading negative 6, it would read 6 amps. Speaking of the lab, we had a setup that was something like this. We had an 8-volt power supply. We had an amp meter, the older analog amp meter. We had a digital amp meter and a resistive load. We should look at this real quick to figure out how many nodes there are. So we'd call this 1, 2, 3. We would call that 4 nodes. Each node is very simple in that there's one input and one output. Since each device only has one input and one output, we can make a statement that the current everywhere in this circuit is the same. So in a series circuit, every element has the same current. We should write that down. In a series circuit, all elements have the same current. And again, this is a series circuit where one occurs after the other. So we have one loop. Every element in the loop has the same current. In that same lab, you connected up power supplies like so, where this was a 25-volt power supply, this was a 25-volt power supply, and you stacked that other independent power supply there. You had the analog meter measuring voltage, and you had the digital meter measuring voltage, and they read the same voltage. And one of the reasons they read the same voltage is because they were on the same node. We would call these 2 voltmeters parallel, whereas we would call the power supplies series connected. We can write a rule here in a parallel circuit. all elements, same voltage. 55 volts here, and you also read 55 volts there. And here, everywhere you looked, you read 800 milliamps in our series circuit. And I believe we already talked about this, the fact that it helps to establish a reference or a ground reference for most of your circuits. That way we always talk about a voltage relative to something else. If you put a voltmeter here, that voltmeter would measure 25 volts with respect to ground. If you put a voltmeter here, it would read 50 volts relative to ground. And if you put a voltmeter here, it would read 55 volts relative to ground. So 55 volts DC, 50 volts DC, and 25 volts DC. Moving on, let's talk about KVL, Kirchhoff's voltage law. And that tells us that the sum of the voltages in a closed loop is 0. You saw this in the lab as well, where you had a power supply set to 8 volts. We had a resistor, a current meter, a resistor, a current meter, a resistor, that large rheostat, remember that's the variable one with the slider that would move back and forth, and one more resistor, like so. And again, that was an ammeter, and that was an ammeter. And I can hear you now, you're like, well, no, we didn't have that many resistors, but, well, kind of you did. Because you had wires connected up, right? These are all the connection wires you used to connect between the ammeters, the power supply, and the rheostat. Oops. Should fix that. There we go. In the lab, you measured the voltage drop across an ammeter, the voltage drop across that old analog meter. You measured the voltage drop across the rheostat, and you measured the voltage drop across each wire. And you said this. You said the voltage on the fluke meter plus the voltage on the analog meter plus the voltage on the rheostat plus the voltage, plus 4 times the voltage on a wire is equal to the supply voltage. Because what we did is we went in an entire loop here, and we declared that the voltages in a closed loop equal 0. By the way, if we took the power supply and we drug it over to the other side, right? If we took this power supply and we said negative Vs equals 0. There it is. That's what it looks like. The summation of the voltages in a closed loop is equal to 0. And when you folks did this in the lab, the numbers were actually very, very close. You were down into the hundredths of a volt. Let's take another look at the definition of a loop. So we'll start with a power supply, a resistor. Okay, that one's not so bad. That loop would simply be this, but let's make it more complicated. We'll add another resistor, and then a third. So now we have 2 loops. So we have loop number 1, and we have loop number 2. But why stop there? We'll add a resistor there. And now we have loop 3. But there's actually one more loop. There is an outer loop as well. So that circuit has 4 loops. And it turns out that KVL is true for every loop. You'll notice that I've made every loop in a clockwise direction. Your author sometimes flips these around, and sometimes will run them in counterclockwise directions. I would strongly suggest that as part of muscle memory, you always make these loops go in a clockwise direction. Let me give you an example of that. Suppose we have an element, and we'll call that element A. We don't know if it's a power supply or a battery, or, well, it doesn't matter. We have an element B. We have an element C, an element D, and an element E. We'll follow the convention described on this meter right here, and we'll use the red probe as a plus. So plus and minus, plus and minus, minus and plus, so on and so forth. Okay, so you can see as we measured our voltages, we weren't very consistent, and we kind of put the probes wherever we wanted them, which makes this problem rather interesting. We'll call this the A loop. We'll call this the B loop. And we are going to take a journey. We're going to start down here, and we're going to walk around the loop. And the rule we'll use is that if we enter on a negative, and we do right here, we start our journey on that negative, we'll put a negative sign in front of the corresponding number. So negative voltage on A, which brings us to this point here. We're continuing our journey. Notice that element B has a positive at that particular location. So we say plus VB, which brings us here now. And the element C has a positive, so that's plus VC. And now we're back where we started, is equal to 0. So that's one loop. The other loop, we'll start here. And again, we'll make that journey. We're entering in on a negative, so we say negative VC. Now we're here. That's another negative, so minus VD. Now we're here. Plus VE is equal to 0. So those are the two equations that describe the voltages in these loops. While we're here, let's do the outer loop. We would record that as negative VA plus VB. That brings us to this point here, entering in another negative, so minus VD. Brings us to here, which is plus VE is equal to 0, because now we're back where we started. So each of these equations describes the voltages using Kirchhoff's voltage law. Again, the summation of the voltages on a closed loop is equal to 0. Let's establish some rules so we're all on the same page. So class rules. Always start in the lower left corner. And always move in a clockwise direction. Here's an example. Power supply, an R1, an R2, and an R3. We start our journey here in the lower left-hand corner, and we travel in a clockwise direction. We're entering on a negative terminal, so we say negative VS plus VR1 plus VR2 plus VR3 is equal to 0. And if you wanted to flip this around, you could say that VR1 plus VR2 plus VR3 is equal to V source, which is what we expected, right? Because we could say that the source, so this is Vs, and all of this on the right side is V load. So supply voltage is equal to the load voltage. We're nearly complete, but I wanted to circle back and go over a few things again. So E, I, R, do you remember what that's called? Right, Ohm's law. And we also talked about PIE. We mentioned that being power. We said that power is equal to a current and a voltage. And using some algebraic manipulation between these two, you could also say that power is I squared R is also equal to E squared divided by R. What I wanted to show you is a circuit where we actually calculate power. So let this be 25 volts DC, and there's a resistor. The resistor is taking electrical energy and it's converting it into heat. And in this case, we'll call it 50 watts. 50 watts of electrical power is being converted into heat. And one of the questions that you might be asked is to find the resistance. I'm going to give you two methods to do this. The first method, a current, is a power divided by a voltage. 50 watts divided by 25 volts. So our current is 2 amps. We know that a resistance is a voltage divided by a current, in this case 25 divided by 2. So the resistance is equal to 12.5 ohms. Method A. Method B, we know that power is equal to a voltage squared divided by a resistance. 50 is equal to 25 squared divided by R. Solving for R, we see that it's 12.5 ohms. Method A required 2 steps. Method B required a single. It's very useful to remember these equations for power. We'll finish off today by talking about constant voltage versus constant current power supplies. We'll let this be our example. We have a source of 100 volts DC. We have a voltmeter, and we have a load that we can change, so a variable load. And our constant voltage supply, the constant voltage supply will do whatever is necessary to keep that voltage constant, which means it will provide whatever current is necessary. So let's make a note of that. So this will provide current to keep constant voltage. And you might ask, well, what range of currents could it take? And it turns out that it could go anywhere from negative infinity all the way up to positive infinity. Here is a circuit for a constant current source, again with a variable load. For sake of discussion, we'll call this 5 amps. The constant current source will provide whatever voltage is necessary to keep the current constant. That voltage could go anywhere from negative infinity all the way to positive infinity. These are mathematical models. When we get to chapter 2, we'll talk about something called Thevenin and Norton. When we get to that point, we'll find out the limitations of real-world supplies. A few examples. If we have 2 ideal power supplies connected in a circuit like so, we'll let this be 18 ohms, 2 volts, 7 volts, DC. we established that we should walk the loop. As we start our journey, we see -2, which brings us to here, where we see -7, plus the voltage on the resistor is equal to 0. So that's Kirchhoff's voltage law. The voltage on the resistor is equal to 9 volts DC, and the current on the resistor is equal to 9 divided by 18, which gives you 1/2 of an amp. Similar circuit on the other side of the house. So let this be 10 amps. Let this be 5 amps. And we'll go to a 2 ohm load. Using Kirchhoff's current law, we would say that the goes intos are 10 plus 5, right? So those currents are going into this node, and then there's one current leaving that node. And we'll call that IR. So the current on the resistor is 15 amps. The voltage on the resistor is 15 amps by 2 ohms. Voltage on that resistor is 30 volts. Here's some things you never want to do. You never want to take 2 ideal power supplies and try to connect them together. That doesn't work. What happens is you can't have a 2-volt node and a 7-volt node attached together. That doesn't make any sense. The nodes can't simultaneously be 2 and 7 volts, and so that circuit blows up. If you try that in the real world, if you take a 6-volt battery and a 12-volt battery and you try to connect them together, they blow up. So don't do that. Don't put sources together unless they have the same voltage. Similar story on this side of the house. You cannot put a 10 amp current source in series with a 5 amp source. This doesn't make any sense. You cannot have a current that is simultaneously 10 amps and 5 amps. So that's no good. However, you can do this. You could put a power supply there. You could put a current source and then a load. So if we call that 10 volts, we call this 2 amps, and we call that 10 ohms. Now in this circuit, we've got the 10 volt supply and the 2 amp supply. And we have to ask ourselves, which one does what? The 10 volt ideal voltage supply will do whatever is necessary to give a current so that the voltage stays at 10. The 2 amp constant current supply will provide whatever voltage is necessary to maintain 2 amps. It turns out that those are compatible. The voltage in this case will simply be 10 volts. And the current on the resistor will be 1 amp. So 10 volts divided by 10 ohms is 1 amp. The power, oh, I'm in the way there. The power will be the voltage squared divided by the resistance, which is 10 squared divided by 10 is 10 watts. Similar story on this side. You can put a voltage source and a constant current source in series. Here we have 10 volts, here we have 2 amps, and 10 ohms. Once again, we have to ask ourselves, what does each device do? The constant voltage source will provide whatever's current necessary to maintain 10 volts across itself, while the constant current source will provide 2 amps no matter what. In this case, the constant current source dominates, so the current on the resistor is 2 amps. The voltage on the resistor is the current multiplied by the resistance, which IR is 2 times 10. So the voltage on the resistor is 20 volts. And the power is equal to I squared R, which is 2 squared by 10. So the power in the resistor is equal to 40 watts. This is a multi-sim simulation of that last circuit we played with. Let's put a voltmeter at this node. By the way, how many nodes are in here? There's the ground or reference node down here, and then there's this node up here. So there's actually only 2 nodes in this circuit. So if we put a voltmeter there, it would be the same as putting a voltmeter there. All right, so there's a voltmeter there. Then we're going to install a current meter. We'll install it here. We'll install one here. And we'll put one more right here. Now, what do you suppose we're going to see? You'll notice this node here, and you'll notice that we've described every current as leaving the node. So the summation of all these should be equal to 0. Let's give it a try and see what we get. So this says that we have 1 amp of current flowing this way. We have negative 2 amps of current flowing this way, which must mean that the current was actually flowing up. And we have 1 amp this way. So if we were to add those together, we would see that the summation of the currents is equal to 0. If it helps, we could flip this around. I think we can do that. Gotta remember how to do that. Flip. There we go. So now we have this current entering the node and these 2 currents leaving the nodes. So now this reads as 2 amps in, 1 amp out that way, and 1 amp out this way. The current is flowing into the power supply, which means that if this was a battery, it would actually be being charged. And here the resistor is dissipating power. This is where it gets fun. Now, this was set to 2 amps, and notice here we have 1 amp out. If we take this and we adjust it to, say, oh, I don't know, let's go to 100 amps. Notice that the resistor here didn't change. There's still 1 amp in that resistor. But look at this. There's now 99 amps flowing into this power supply or this battery. The same thing would happen if we took this current and we changed the sign on it. So negative 100. There we go. We still have 1 amp here, but now there's negative 101 amps going into the battery. And we established that a constant voltage supply will do whatever is necessary, which is to say it'll provide whatever's current necessary to keep the voltage across it at, in this case, 10 amps. Whereas the constant current source will simply give that particular current, and it can go to any voltage necessary to make that happen. So again, these 2 are compatible. I'll show you the incompatible situation. If we copy this source, so duplicate, we're going to connect it up. Oops. So we'll connect that. We'll connect that. We'll delete that. And we'll set this one to 100 volts. So we have one supply with 10 volts and one at 100. Let's see what the simulation does. Oops. Parallel voltage source found. So it won't run the simulation. It basically crashed out of it. Said it cannot do it. And it can't, because you cannot have this node up here simultaneously at 10 volts and at 100 volts. That just doesn't work. That's it for today. If you have any questions, you can leave them down below, or you can post them on the class page.